Close your eyes for a moment and imagine something with me. Imagine a ship, not a boat on the ocean, not an airplane crossing a continent, but something so vast, so impossibly enormous, that it makes an aircraft carrier look like a toy floating in a bathtub. This ship is 10 kilometers long. That is longer than Manhattan Island from tip to midpoint. It weighs millions of tons. It carries 10,000 human beings inside its rotating hull, along with forests, farms, rivers of recycled water, and an atmosphere manufactured by machines that must never ever stop working. This ship is not orbiting Earth. It is not parked near the moon. It is hurtling through the absolute blackness between stars at roughly 3% of the speed of light, which sounds fast until you realize that even at that staggering velocity, the nearest star system is still over a century away. The people on board this ship were not born on Earth. Their parents were not born on Earth. In fact, no living person on this ship has ever seen a sunrise, felt rain on their face, or breathed air that was not recycled through the same mechanical lungs that have been breathing for them since before anyone alive can remember. This ship left Earth 170 years ago. It will not arrive at its destination for another 80 years, and something is going wrong. The oxygen readings in Sector 7 have been dropping, not dramatically, not in a way that triggers the emergency alarms, but slowly, quietly, like a whisper you cannot quite hear. 0.5% this year, 1/3% last year. The agricultural domes in the aft section reported a fungal infection 3 months ago. It was contained, they said, but the soybean yield is down 12%, and nobody can explain why the wheat in Dome 4 tastes slightly different than it did a decade ago. There was a fight in the Commons last week. 2 families from different work rotations. It started over water rations and ended with a broken arm and a disciplinary hearing. The ship's doctor reported that she has seen a 17% increase in depression diagnoses among the 16 to 25 age group this quarter. And there is a rumor, spreading quietly through the lower decks, that the navigation computer made a correction last month that no one authorized and no one can fully explain. No one is panicking yet. These are small problems, manageable problems, the kind of problems that a well-designed ship with well-trained crews should be able to handle. But here is the thing that no one on this ship knows, the thing that makes this story not just a thought experiment but a scientific near certainty. These are not separate problems, they are symptoms. Symptoms of a disease that has been building since the day this ship left Earth. A disease that is woven into the laws of physics, into the nature of biology, into the architecture of the human mind itself. And it is terminal. Today we are going to take a journey, not to the stars, but into the science of why getting to the stars might be the most terrifying thing humanity could ever attempt. We are going to examine, with brutal scientific honesty, why the Generation ship, humanity's most romanticized and celebrated concept for interstellar travel, would almost certainly become a tomb. A coffin drifting through the void between stars, carrying the frozen remains of a civilization that thought it could outsmart the universe. This is not science fiction doom and gloom. This is physics. This is biology. This is psychology. This is thermodynamics. And every single one of these disciplines is screaming the same warning at us, a warning that we desperately need to hear before we ever attempt to build such a vessel. Before we dive in, I want you to consider 2 facts. Just 2. The first is this. In 1991, a team of scientists and engineers built the most sophisticated sealed ecosystem ever constructed on Earth. It was called Biosphere 2, and it was located in Oracle, Arizona. It was a massive glass and steel structure, covering over 12,000 square meters, containing multiple biomes including a rainforest, an ocean, a desert, and agricultural land. They sealed 8 human beings inside this structure, with the goal of maintaining a completely self-sustaining ecosystem for 2 years. Just 2 years. Just 8 people. On Earth, with hospitals nearby, with the ability to pump in emergency oxygen if needed, with the full support of a $1 billion research program. Within 16 months, the oxygen levels inside Biosphere 2 had dropped from the normal 20.9% to 14.5%. That is equivalent to trying to breathe at 15,000 feet altitude. The crew members were gasping for air, suffering from chronic fatigue and experiencing cognitive impairment. They were starving because crop yields were 50% lower than expected. Cockroaches and crazy ants had exploded in population, while most of the pollinating insects had died. And the 8 crew members, who had started as friends and colleagues, had split into 2 hostile factions that refused to speak to each other. The experiment was considered a failure on almost every metric. The second fact: NASA conducted a landmark study called the Twin Study, in which astronaut Scott Kelly spent approximately 1 year aboard the International Space Station, while his identical twin brother Mark Kelly remained on Earth. When Scott returned, researchers discovered that his DNA had been measurably altered. His telomeres, the protective caps on the ends of chromosomes, had lengthened in space and then shortened dramatically upon return. His gene expression had changed. Hundreds of genes related to his immune system, bone formation, and DNA repair had been switched on or off in ways that were different from his brother. His cognitive performance had declined. And this was after just 1 year, in low Earth orbit, protected by the remnants of Earth's magnetic field, with regular resupply of food, water, and air from the planet below. Now take both of those facts and multiply them. Multiply the sealed ecosystem problem by a factor of 100, because a generation ship must maintain its ecosystem, not for 2 years, but for 250 years. Not for 8 people, but for 1,000 or more. Not on Earth with backup options, but in the absolute void of interstellar space where no rescue is possible. Multiply the biological damage by 10 generations of human beings, each one born into an environment of elevated radiation, artificial gravity, recycled air, limited genetic diversity, and psychological pressure that no human being has ever been designed to endure. When you do that multiplication, when you honestly and rigorously follow the science wherever it leads, you arrive at a conclusion that is as inescapable as it is terrifying. Generation ships would become tombs. Let me take you through exactly why, step by step, system by system, and let me show you how the universe itself conspires against this dream. Let us start with the most fundamental question. What exactly is a generation ship, and why would we ever need one? The concept is elegant in its simplicity and horrifying in its implications. A generation ship is a spacecraft designed to carry human beings across interstellar distances that are so vast, the journey will take not years, not decades, but centuries. The original crew who depart from Earth will grow old and die aboard the ship. Their children will be born aboard the ship, live their entire lives aboard the ship, and die aboard the ship. Their grandchildren and great-grandchildren will do the same, generation after generation, century after century, until finally some distant descendant of the original crew arrives at the destination star system, and presumably sets foot on a new world. The people who launch the ship will never see the destination. The people who arrive at the destination will never have seen Earth. The reason we would need such a vessel comes down to a simple and brutal fact about the universe we live in. The distances between stars are, to put it in the most precise scientific language available, absolutely insane. The nearest star system to our Sun is Proxima Centauri, part of the Alpha Centauri triple star system, and it is 4.24 light-years away. A light-year is the distance that light, the fastest thing in the universe, travels in 1 year. Light moves at approximately 300,000 kilometers per second. In 1 year, it covers about 9.5 trillion kilometers. Multiply that by 4.24, and you get the distance to our nearest stellar neighbor, roughly 40 trillion kilometers. To put that in perspective, if you could drive a car at highway speed non-stop, it would take you about 50 million years to get there. Now, our fastest spacecraft ever built, the Parker Solar Probe, has reached speeds of about 635,000 kilometers per hour relative to the Sun, making it the fastest human-made object in history. Even at that incredible velocity, it would take the Parker Solar Probe approximately 7,000 years to reach Proxima Centauri. 7,000 years. That is longer than all of recorded human civilization. The Voyager 1 probe, launched in 1977, and now the most distant human-made object from Earth, is traveling at about 61,000 kilometers per hour. At that speed, it would take Voyager roughly 73,000 years to reach Proxima Centauri if it were heading in that direction, which it is not. So, let us be realistic about what interstellar travel actually means. Even with optimistic projections of future propulsion technology, nuclear pulse propulsion like the theoretical Project Orion concept, or fusion drives like the British Interplanetary Society's Project Daedalus, or laser-pushed light sails. The realistic speed range for a large crewed spacecraft is somewhere between 1 and 5% of the speed of light. At 1% of light speed, which is 3,000 kilometers per second, the trip to Proxima Centauri takes about 424 years. At 5%, it takes about 85 years. Most engineering analyses, including those from the recent Project Hyperion competition organized by the Initiative for Interstellar Studies, assume a journey time of approximately 250 years, which corresponds to a cruise speed of roughly 1.5 to 2% of light speed. 250 years, 10 human generations. That is approximately the same span of time that separates us from the American Revolution, from the reign of King George III, from a world where the fastest mode of transport was a horse, and the most advanced communication technology was a hand-delivered letter. The people who would arrive at the destination of a generation ship launched today would be as far removed from us, culturally, psychologically, and potentially even biologically, as we are from the colonial settlers of the 1770s. And every single day of those 250 years, every hour, every minute, the ship must function perfectly. Not well, not adequately, perfectly. Because there is no rescue, there is no resupply, there is no port where you can pull in for repairs. There is no hospital ship you can call. There is nothing but void, radiation, and cold. This is the tyranny of distance, and it is only the beginning of the nightmare. Why can we not simply go faster? This is the question that every child asks and every physicist dreads, because the answer involves one of the most unforgiving equations in all of engineering. It is called the Tsiolkovsky rocket equation, and it is the reason that interstellar travel is so monstrously difficult. The equation tells you that the amount of fuel you need for a journey grows exponentially with the desired velocity, not linearly, exponentially. If you want to go twice as fast, you do not need twice as much fuel. You need vastly more, because you have to carry the fuel to accelerate the fuel that will accelerate the fuel. And at the end of the journey, if you want to slow down at your destination rather than fly through the star system at 3% of light speed, you need to carry deceleration fuel too, which means you need even more fuel to accelerate that deceleration fuel at the start. The mass ratios become absurd. For a fusion-powered generation ship carrying 1,000 people with all their life support and habitat infrastructure, achieving even a few percent of light speed and then decelerating at the destination would require fuel masses that dwarf the payload by orders of magnitude. We're talking about a ship where 90% or more of the total mass at departure is fuel. This creates a terrible paradox. To minimize the time your crew spends exposed to the hazards of interstellar space, you want to go fast. But to go fast, you need more fuel, which means a bigger ship, which means more structural mass, which means more fuel to move that structure, which means an even bigger ship. At some point, the engineering becomes physically impossible. You cannot build a ship large enough to carry the fuel needed to move a ship that large. This is not a technology problem. This is not something that better engines will solve. This is a fundamental constraint imposed by the laws of physics themselves. You can reduce it with more efficient propulsion, with lighter materials, with external propulsion like laser sails, but you cannot eliminate it. The universe has placed a hard speed limit on how fast a massive object can travel between stars, using any propulsion system that obeys the known laws of physics, and that speed limit means journey times measured in centuries. But let us set aside the propulsion problem for now. Let us be generous. Let us assume that some future engineering breakthrough allows us to build a ship capable of sustained 1.5 to 2% light speed with deceleration at the destination. Let us assume the ship is built, fueled, and launched successfully. The journey has begun. 10,000 human beings are sealed inside a rotating cylinder hurtling through the darkness at 6,000 kilometers per second. Now what? Now the universe starts trying to kill them. And it starts with something they cannot see, cannot feel, cannot taste, and cannot hide from. Cosmic radiation is the silent executioner of deep space, and it is perhaps the single most intractable problem facing any generation ship concept. To understand why, you need to understand what cosmic radiation actually is, and why Earth is such a uniquely protected environment. Our planet sits inside a cocoon of protection that most people never think about. The Earth's magnetic field, generated by the churning iron core far beneath our feet, extends tens of thousands of kilometers into space, creating a vast magnetic bubble called the magnetosphere. This magnetosphere deflects the vast majority of charged particles streaming in from the Sun and from the wider galaxy. On top of this, our atmosphere, that thin blue line visible from orbit, provides an additional layer of shielding equivalent to about 10 meters of water. Together, these two shields reduce the radiation exposure at Earth's surface to a tiny fraction of what exists in open space. In interstellar space, both of these shields are gone. There is no magnetosphere, there is no atmosphere, and the radiation environment is dominated not by the relatively gentle solar wind, but by galactic cosmic rays, or GCRs. These are particles, mostly protons but also heavier atomic nuclei, stripped of their electrons, that have been accelerated to tremendous energies by supernova explosions, neutron star collisions, and the violent electromagnetic environments near black holes. Some GCRs carry energies millions or even billions of times greater than anything produced by the Sun. They travel at velocities very close to the speed of light, and they are extraordinarily penetrating. A single high-energy iron nucleus cosmic ray can pass through several meters of solid metal. When a GCR strikes the hull of a spacecraft, something deeply counterintuitive happens. You might think that thicker shielding means better protection, and for low-energy particles that is true, but for the highest energy GCRs, hitting a metal hull does not stop them cleanly. Instead, the impact shatters both the incoming particle and the atoms of the hull into a shower of secondary particles through a process called spallation. These secondary particles include neutrons, pions, gamma rays, and lighter charged fragments, and they spray inward like shrapnel from an explosion. In many cases, the secondary radiation produced by the shielding is actually more biologically damaging than the original cosmic ray would have been if it had passed through unshielded. This means that simply piling on more metal armor can actually make the radiation problem worse, not better. It is one of the cruel ironies of physics. To bring the radiation environment inside a spacecraft down to Earth-like levels, you would need shielding equivalent to approximately 5 meters of water or rock surrounding the entire habitable volume. For a generation ship housing 1,000 people with the necessary agricultural space, living quarters, common areas, machinery rooms, and infrastructure, the habitable volume would be enormous. Surrounding all of that with 5 meters of water, or equivalent mass, would add millions of tons to the ship's mass, making the propulsion problem exponentially worse. Magnetic shielding, using powerful superconducting magnets to deflect charged particles, has been proposed as an alternative, but it requires enormous amounts of power. The magnets themselves are massive and fragile, and the highest energy GCRs are so energetic that no practical magnetic field can deflect them significantly. So what happens to the human beings inside a generation ship that cannot fully shield against cosmic radiation? The answer unfolds over generations, and it is insidious. In deep interstellar space, the radiation dose from GCRs is approximately 1 to 2 millisieverts per day. For comparison, the average person on Earth receives about 2.4 millisieverts per year from all natural background sources. That means a generation ship crew would be receiving in a single day what an Earth dweller receives in an entire year. Over a human lifetime of 70 years, that exposure adds up to roughly 25 to 50 sieverts. To put that in perspective, a total body dose of 5 sieverts delivered all at once is almost always fatal. The chronic low-dose exposure on a generation ship would not kill anyone that quickly, but it would dramatically increase the rates of cancer, cataracts, cardiovascular disease, and neurological degeneration. It would damage reproductive cells, increasing the rate of mutations passed to offspring, and over 10 generations, those mutations would accumulate. But it is not just the humans who suffer. Every living thing on the ship is being irradiated. The crops in the agricultural domes, the bacteria in the water recycling systems, the microorganisms in the soil, the insects needed for pollination. All of them are accumulating radiation damage. All of them are mutating faster than they would on Earth, and all of them are evolving in an environment that has never existed before in the history of life. The bacteria are of particular concern because bacteria reproduce so much faster than humans, completing a generation in minutes or hours rather than decades. Over 250 years, bacteria on a generation ship would go through millions of generations of evolution. in an elevated radiation environment. The potential for the emergence of novel, antibiotic-resistant, highly virulent pathogens is not just theoretical, it is, according to NASA research on the International Space Station, already happening on a small scale. Bacteria on the ISS have been observed to mutate more rapidly and to develop increased virulence compared to their Earth-based counterparts. Scale that up to a quarter millennium, and the medical implications are staggering. Now, let me talk about something that might sound less dramatic than cosmic radiation, but is in many ways even more terrifying because it is so much more subtle and so much harder to solve. I want to talk about the air you breathe. On Earth, the atmosphere maintains itself through billions of years of evolved biogeochemical cycles. The carbon cycle, the nitrogen cycle, these are not simple systems. They involve the interaction of trillions of organisms across every ecosystem on the planet, mediated by geological processes, ocean currents, volcanic activity, and the energy of the sun. The concentration of oxygen in Earth's atmosphere has remained remarkably stable at approximately 20.9% for hundreds of millions of years. The concentration of carbon dioxide has fluctuated, but within ranges that life can tolerate. This stability is not accidental. It is the product of a planetary-scale feedback system of almost incomprehensible complexity. A generation ship must replicate the system in a sealed metal container, and it must do so perfectly for 250 years, with no margin for error, because atmospheric composition is not something that degrades gracefully. You do not slowly get a little bit uncomfortable as oxygen drops. Human beings are exquisitely sensitive to atmospheric changes, and the effects are nonlinear. At 20.9% oxygen, you are fine. At 19%, most people would not notice anything. At 17%, you start to experience impaired judgment and coordination. At 16%, you are struggling to think clearly. At 14%, you are experiencing serious cognitive impairment, fainting, and risk of death. At 12%, you lose consciousness within minutes. At 10%, you are dead. That is a window of just a few percentage points between normal function and death. And here is the truly terrifying part. Carbon dioxide is even more dangerous because its effects begin at much lower concentrations. On Earth, atmospheric CO2 is about 400 parts per million, or 0.04%. At 1% CO2, people begin to feel drowsy. At 2%, you experience headaches, increased heart rate, and difficulty concentrating. At 5%, you are in serious danger. At 8%, you lose consciousness. And unlike oxygen depletion, which at least gives you the obvious symptom of breathlessness, CO2 buildup is sneaky. It impairs your cognitive function before you realize anything is wrong. You become stupid before you become dead, which means you lose the ability to diagnose and fix the problem before you lose the ability to breathe. Now, consider the Biosphere 2 disaster through this lens. The engineers and scientists who designed Biosphere 2 were not amateurs. They were among the best in the world at ecological engineering. They spent years designing the system, carefully balancing the plant life against the human inhabitants, calculating carbon and oxygen budgets, selecting species for each biome. And they still got it catastrophically wrong. The problem turned out to be something no one had anticipated. The unsealed concrete in the structure was absorbing carbon dioxide through a chemical reaction called carbonation, which effectively removed CO2 from the atmosphere. Normally, this would be fine because plants would compensate by producing more CO2 through respiration at night. But the soil in Biosphere 2 was extremely rich in organic matter, and the soil microbes were consuming oxygen at a rate far higher than predicted. So oxygen was being consumed by soil microbes, CO2 was being absorbed by concrete, and the whole atmospheric balance was spiraling out of control in a way that no one had modeled because no one had tested a system this complex before. On a generation ship, the atmospheric problem is orders of magnitude worse. First, you're operating the system not for 2 years, but for 250. Small imbalances that are negligible over months become lethal over decades. A recycling inefficiency of 0.1% per year means a 1% loss per decade, a 10% loss per century, and total system collapse well before the 250-year mark. Second, you do not have the luxury of pumping in emergency oxygen from outside, as was eventually done at Biosphere 2. There is no outside. There is only vacuum. Third, The system is more complex because it must support more people, and the feedback loops between human respiration, plant photosynthesis, soil microbiology, water chemistry, and atmospheric gas exchange are more numerous and more tightly coupled. One failure cascades into another. A crop blight reduces plant photosynthesis, which reduces oxygen production, which reduces the air quality for the humans who must tend the next crop, which reduces their cognitive function and physical health, which reduces their ability to manage the agricultural systems, which leads to further crop decline. It is a death spiral, and once it starts, it may be very difficult to stop. Let me go deeper into the agricultural nightmare, because food production on a generation ship is perhaps the most underappreciated challenge in all of interstellar travel planning. On Earth, agriculture seems simple. You put seeds in dirt, add water and sunlight, and food grows. But that simplicity is an illusion supported by an entire planet's worth of infrastructure that we take for granted. Earth's soil is not just dirt. It is a living ecosystem containing billions of organisms per teaspoon, bacteria, fungi, nematodes, arthropods, all working together in a network of nutrient cycling that has been evolving for 400 million years since plants first colonized land. The soil breaks down dead organic matter and returns nutrients to a form that plant roots can absorb. Mycorrhizal fungi form symbiotic networks with plant roots, extending their reach and delivering phosphorus and other minerals in exchange for sugars. Nitrogen-fixing bacteria convert atmospheric nitrogen into ammonia that plants need for growth. Earthworms aerate the soil and mix organic matter through its layers. Without these organisms, soil is just sterile mineral particles, and plants cannot grow in it. A generation ship must carry all of these organisms and maintain their populations in balance for a quarter millennium. If the mycorrhizal fungi die, plants lose access to phosphorus and their yields drop. If the nitrogen-fiction bacteria populations crash, nitrogen becomes unavailable and crops fail. If earthworm populations are lost, soil compaction reduces root growth and water infiltration. And every one of these organisms is subject to the same evolutionary pressures as every other living thing on the ship: mutation from cosmic radiation, genetic drift from small populations, and adaptation to an artificial environment that bears little resemblance to any ecosystem on Earth. Then there is the pollination problem. Roughly 75% of the world's food crops depend on animal pollinators, primarily bees. On Earth, pollination is handled by thousands of species of bees, butterflies, moths, flies, bats, and birds, providing a deep web of redundancy. If one pollinator species declines, others can partially compensate. On a generation ship, you might carry a few species of bees. If those bees die, and we have seen dramatic bee die-offs on Earth due to pesticides, disease, and habitat loss, your food production collapses. You could hand-pollinate, as farmers in some parts of China already do due to bee losses, but hand-pollinating enough crops to feed 1,000 people is an enormous labor burden on a crew that already has countless other critical tasks. The soil degradation problem is particularly insidious. On Earth, soils are renewed through weathering of rocks, deposition of sediments by water and wind, addition of organic matter from dead plants and animals, and the slow geological processes that cycle nutrients from deep underground to the surface. On a generation ship, there is no geological cycle. The soil you launch with is all the soil you will ever have. Over decades and centuries of continuous cultivation, that soil will lose nutrients, accumulate toxins, change in pH, lose organic matter, and become increasingly hostile to plant growth. You can compost human and plant waste to return some nutrients, but the recycling is never 100% efficient. Some nutrients will be locked up in forms that plants cannot access. Some will be lost through chemical reactions, through the water recycling system, through human metabolic processes. The soil will slowly die, and as it dies, so does the food supply. Consider also the light energy problem. In interstellar space, there is no sunlight. There is no star within useful range to provide photosynthetic energy. All light for plant growth must come from artificial sources, which means enormous banks of high-intensity grow lights powered by the ship's electrical systems. Growing enough food for 1,000 people requires roughly 200 to 500 kilowatts of continuous lighting power, depending on the efficiency of the lighting and the crops grown. This is on top of all the other power demands of the ship: life support, water recycling, heating, cooling, rotation mechanisms, computers, communications, manufacturing, medical equipment. The total power demand for a generation ship is estimated at several megawatts continuous, and that power must be generated reliably for 250 years without a single prolonged interruption. We will discuss the terrifying implications of that requirement when we get to the engineering section. I also need you to understand something about disease on a generation ship that is fundamentally different from disease on Earth, and it goes beyond the mutation and evolution of pathogens that I mentioned earlier. It has to do with the human immune system and how it develops. On Earth, human beings are exposed from birth to an enormous diversity of microorganisms. We encounter soil bacteria, airborne fungi, viruses from other humans and animals, parasites from food and water, and thousands of other pathogens that our immune systems learn to recognize and fight. This constant exposure trains and maintains our immune systems, keeping them vigilant and effective. It is why children who grow up on farms tend to have stronger immune systems and fewer allergies than children raised in sterile urban environments. Exposure to microbial diversity is essential for immune health. On a generation ship, the microbial environment is impoverished. The initial crew will carry their own microbiomes, but over generations in a sealed environment with limited microbial diversity, those microbiomes will simplify. The immune systems of shipborne humans will be trained on a much smaller set of organisms. They will become specialists, very good at fighting the specific microbes present on the ship, but potentially helpless against anything new. And here is where the nightmare connects back to the mutation problem. If a novel pathogen evolves from the ship's existing microbial population, a new strain of bacterium or virus that the population has no evolutionary defense against, it will spread through a community of immunologically naive people in a closed environment with recycled air. This is the recipe for a pandemic that makes anything Earth has ever experienced look mild by comparison. On Earth, a pandemic can be mitigated by quarantine, by geographic isolation, by the sheer distance between populations. On a generation ship, there is nowhere to quarantine. There is no geographic isolation. Everyone breathes the same recycled air. Everyone drinks the same recycled water. An airborne pathogen could infect the entire population within days. History gives us a chilling preview of what happens when isolated populations encounter novel diseases. When European explorers reached the Americas, the indigenous populations had been isolated from Eurasian disease pools for thousands of years. The result was a biological catastrophe. Smallpox, measles, influenza, and other diseases killed an estimated 50 to 90% of the indigenous population within a few generations. The generation ship population, after 200 years of isolation, would be in an analogous position, not with respect to Earth diseases, but with respect to whatever novel pathogens their own sealed ecosystem has brewed up over the centuries. Let me move now from the external threats to something even more intimate and even more disturbing. Let me talk about what happens to the human genome itself on a generation ship. This is the genetic death spiral, and it is one of the most scientifically robust arguments against the viability of generation ships. Every species needs genetic diversity to survive over long time periods. Diversity is not a luxury, it is a survival mechanism. When a population has high genetic diversity, it means that different individuals carry different versions of genes, different alleles, that confer different advantages and vulnerabilities. If a new disease appears, some individuals will have genetic resistance, and the population survives. If environmental conditions change, some individuals will be better adapted, and the population persists. Genetic diversity is the raw material of evolution, the toolkit that allows life to adapt to challenges it has never faced before. When a population is small and isolated, genetic diversity erodes through a process called genetic drift. In a large population of millions, the random fluctuations in which alleles get passed to the next generation average out. Rare alleles are maintained because the law of large numbers protects them. In a small population, random chance dominates. An allele carried by only a few individuals can be lost in a single generation, simply because those individuals happen not to have children, or their children happen not to inherit that particular allele. Over many generations, this random loss accumulates. The population's genetic toolkit gets smaller and smaller, like a library that loses a few books every year. After enough time, what is left is impoverished, fragile, and vulnerable. The mathematical framework for understanding this is well established. Conservation biologists use something called the 5500 rule. You need at least 50 breeding individuals to prevent serious inbreeding depression in the short term, and at least 500 to maintain genetic diversity over the long term. But these numbers are absolute minimums for bare survival, not for a healthy, thriving population. Cameron Smith, an anthropologist at Portland State University who has studied this question extensively in the context of the Project Hyperion generation ship design, published a landmark paper in Acta Astronautica in 2014, arguing that a genetically viable population for a multi-generational interstellar voyage would need to be in the tens of thousands, not the hundreds or low thousands that most generation ship designs assume. His analysis accounted for the risk of catastrophic events, disease outbreaks, accidents that could kill significant portions of the population, and the normal fluctuations in birth and death rates that affect small populations. The Project Hyperion competition set its population constraint at 1,000 plus or minus 500, based on earlier, more optimistic estimates. But Smith's work and subsequent simulations suggest this may be dangerously low. There is a phenomenon in genetics called Müller's ratchet, named after the Nobel Prize-winning geneticist Hermann Müller, and it is particularly relevant to a generation ship. Müller's ratchet describes the process by which harmful mutations accumulate irreversibly in small populations. In a large population, natural selection can efficiently remove harmful mutations because there are always plenty of mutation-free individuals to outcompete the mutant ones. But in a small population, random drift can fix harmful mutations in the gene pool faster than selection can remove them. Each generation loses a few more well-functioning gene variants and gains a few more deleterious ones. The ratchet only turns one way. You can lose genetic quality, but in a small closed population, you can never regain it. Over 10 generations in a population of a few hundred or a few thousand, this ratchet can produce a measurable decline in overall genetic fitness, increased susceptibility to disease, reduced fertility, developmental abnormalities, cognitive decline. Now combine this with the elevated mutation rate from cosmic radiation. Every generation, the cosmic rays are introducing new mutations into the gene pool at a rate higher than on Earth. Most mutations are neutral or harmful. Beneficial mutations are extremely rare. In a small population already suffering from genetic drift and the loss of diversity, the influx of radiation-induced mutations does not replenish what has been lost. It adds noise. It adds errors. It accelerates the decay. The real-world examples of what happens to small isolated populations are grim. The cheetah, which passed through a severe population bottleneck thousands of years ago, has such low genetic diversity that individuals can accept skin grafts from unrelated cheetahs without immune rejection, something that would be impossible in a genetically healthy species. Cheetahs suffer from high infant mortality, low sperm quality, and vulnerability to disease. The Tasmanian devil is being driven toward extinction by a transmissible facial tumor that is only possible because the population's genetic diversity is so low that the animal's immune systems cannot distinguish the tumor cells from their own tissue. The Habsburg dynasty of European royalty practiced extensive intermarriage and produced a lineage of increasing physical deformity, infertility, and early death. Charles II of Spain, the last of the Spanish Habsburgs, was so inbred that his coefficient of inbreeding was higher than that of a child born to a brother and sister. He was mentally and physically disabled, unable to chew food properly due to his malformed jaw, and died at age 38 without producing an heir. On a generation ship, even with carefully managed breeding programs using genetic algorithms to maximize diversity, the fundamental problem remains. The starting population carries only a tiny fraction of the total human genetic diversity on Earth, estimated at about 0.1% variation between any two humans, but distributed across billions of people. A founding population of 1,000 carries an even tinier sampling of that diversity, and then the ratchet begins to turn. There is a potential mitigation. You could carry frozen sperm, eggs, and embryos from a much larger population, effectively creating a genetic bank that supplements the living population's diversity. This is a sound idea in principle, but it requires cryogenic storage systems that function perfectly for 250 years. The longest we have successfully stored viable frozen human sperm on Earth is a few decades. Eggs and embryos are even more fragile. The cryogenic storage must be maintained at extremely low temperatures, typically minus 196 degrees Celsius, using liquid nitrogen. On a generation ship, the liquid nitrogen must be produced, stored, and replenished continuously for a quarter millennium. Any power failure that allows the storage temperature to rise even briefly could destroy the entire genetic bank. You have put all your eggs, quite literally, in one extremely fragile basket. And even if the genetic bank survives, using it requires reproductive technology, artificial insemination, in vitro fertilization, embryo implantation that must also function perfectly for 250 years. The equipment must be maintained. The chemicals and media must be manufactured or stored. The medical personnel must be trained. Every generation must have the knowledge, the tools, and the willingness to use reproductive technology to supplement natural reproduction with genetic bank material. If any generation abandons this practice through cultural drift, religious prohibition, social resistance, or simply losing the technical knowledge, the genetic safety net disappears. This brings us to what I consider the most underappreciated threat to any generation ship. Not physics, not biology, not engineering, but psychology. The human mind is simultaneously humanity's greatest tool and its most fragile component, and the conditions inside a generation ship are precisely calibrated, as if by a malevolent designer, to break it. Let me take you through this carefully, because I want you to truly understand the depth of the psychological horror that a generation ship represents. Start with the basic conditions. You are inside a sealed metal cylinder. The walls are your entire world. You will never feel wind on your face unless it comes from a ventilation fan. You will never see a horizon. You will never experience weather. The sky above you, if your ship is large enough to have one, is the underside of the opposite wall of the rotating cylinder, visible through the simulated atmosphere, curving up and over your head in a way that would deeply unsettle any human being accustomed to the flat or gently curved horizon of a planetary surface. The light comes from artificial sources on a programmed cycle. The food comes from the agricultural domes. The water comes from the recycling systems. Everything is controlled. Everything is artificial. Everything is enclosed. Now layer on the social conditions. You know everyone on this ship. Not casually. Not the way you know people in a city, where you are surrounded by millions of strangers. You know everyone, because there are only a few hundred or a few thousand people, and you have known most of them since birth. There are no new faces. There will never be new faces. The person you marry will be chosen, at least in part, by a genetic algorithm. The job you do will be assigned based on the ship's needs, not your interests. Your children's lives will be planned before they are born, and you know with absolute certainty that you will die inside this ship. You will never reach the destination. Your grandchildren might, or their grandchildren, but you are here to work, to breed, to maintain systems, and to die. That is your entire purpose. The Mars 500 experiment in Moscow from 2010 to 2011 gave us a small window into what prolonged isolation does to human psychology. 6 men were sealed inside a 550 cubic meter facility for 520 days, simulating a round-trip mission to Mars. The facility was far more spacious, per person, than any generation ship would be. The crew was composed of highly motivated, carefully screened volunteers who had chosen to participate. They knew the experiment had an end date. They had communication with the outside world, albeit with a simulated time delay. And still, the results were disturbing. Multiple crew members developed depression. Sleep cycles became severely disrupted, with one crew member spending increasingly long periods in bed, sometimes sleeping 18 hours a day. Interpersonal conflicts increased over time, motivation and productivity declined. And this was 520 days with 6 people who knew it would end. Now multiply that by a lifetime, by 10 lifetimes. Consider the generation ship crew member who is born, grows up, works, grows old, and dies all inside the same metal cylinder, knowing from childhood that this is all there will ever be. The existential weight of that is almost incomprehensible. Psychologists have identified what they call the middle generation problem, and it may be the single most powerful argument against generation ships from a human perspective. The first generation on a generation ship has purpose. They were born on Earth. They remember blue sky, oceans, forests, the richness and variety of a living planet. They volunteered for this mission because they believe in its importance. They carry the dream. They have something to leave behind and something to work toward. Their motivation is intrinsic and powerful. The last generation also has purpose, perhaps even more than the first. They are the ones who will arrive. They will see the new star growing brighter in the forward windows. They will orbit a new world. They will be the first humans to set foot on an alien planet. Their entire lives have been building toward this moment, and the culmination is within reach. They have hope, excitement, anticipation. But the middle generations have nothing. They were not born on Earth. They carry no memories of blue sky or open water. They will not see the destination. They are born, they work, they are told to reproduce according to the genetic management plan, and they die. Their entire existence is to be a link in a chain, a maintenance crew for a ship that someone else designed and someone else will benefit from. They are, in the most literal sense, born into service of a mission they did not choose, cannot leave, and will never see completed. Philosopher Neil Levy has written extensively about the ethical implications of this situation. He argues that it is fundamentally immoral to create human beings whose life choices are so severely constrained by the circumstances of their birth. On Earth, even people born into poverty or oppressive regimes have the theoretical possibility of escape, of migration, of revolution. On a generation ship, there is no escape. You cannot emigrate. You cannot go outside. The nearest habitable environment is decades away at the ship's current velocity. You are trapped, and every generation after the first is trapped by a decision they had no part in making. The psychological consequences of this are predictable and terrifying. Depression, nihilism, suicidal ideation, substance abuse, if any intoxicating substances can be manufactured or grown on the ship, social withdrawal, and critically, loss of motivation to perform the maintenance and technical work that keeps the ship alive. If even a small percentage of the middle generation decides that the mission is not worth their suffering, that they owe nothing to descendants they will never meet, the consequences for ship maintenance could be catastrophic. Deferred maintenance, careless repairs, deliberate sabotage, all become possibilities when people feel they have nothing to live for. History offers us a grim analogy in the social dynamics of small, isolated, confined populations. In 1790, 9 mutineers from HMS Bounty, along with 6 Polynesian men and 12 Polynesian women, settled on Pitcairn Island, one of the most remote inhabited places on Earth. The population started at 27 people. Within 4 years, the settlement had descended into murder, factional warfare, alcoholism, and sexual violence. By 1800, just 10 years after settlement, only 1 of the 9 original mutineers was still alive. Most of the Polynesian men had been murdered, and the surviving community was deeply traumatized. In 2004, more than 2 centuries later, Pitcairn Island was shaken by a sex abuse scandal that revealed systematic abuse within the tiny community of fewer than 50 people. The isolation, the small population, the inability to leave, the lack of external oversight had created conditions where deeply dysfunctional social norms had taken root and persisted for generations. A generation ship is Pitcairn Island writ large, sealed in a metal shell, hurtling through the void, with no possibility of intervention from outside. The social dynamics that destroyed Pitcairn's community in 10 years would have 250 years to play out on a generation ship. And then there is the question of violence. It is a simple statistical fact that there has been no 250-year period in recorded human history that was free of significant violent conflict. Empires rise and fall, revolutions erupt, civil wars tear societies apart, religious conflicts, ethnic conflicts, class conflicts, ideological conflicts. All of these are persistent features of human social organization, especially under conditions of resource scarcity and confined living. On a generation ship, all the ingredients for conflict are present. Limited resources that must be rationed, social stratification based on job assignments, reproductive control that removes individual autonomy, generations of people who feel trapped and purposeless, authority structures that must maintain control for centuries. Every one of these is a pressure point, and eventually one or more of them will crack. The consequences of violence on a generation ship are uniquely catastrophic because the ship is a pressurized vessel surrounded by vacuum. A bullet hole in the hull is not just property damage, it is a potential decompression event that could kill everyone in that section. An explosion in a fight near a critical system could take out life support for the entire ship. Even a fistfight near the wrong control panel could trigger a cascade failure. On Earth, the worst that a bar fight can do is send a few people to the hospital. On a generation ship, a bar fight near the water recycling control room could end civilization. So how do you prevent violence for 250 years? The obvious answer is authoritarian control. Strict hierarchy, surveillance, severe punishments, absolute authority vested in a captain or council. But authoritarianism creates its own problems. It breeds resentment. It concentrates power in the hands of individuals who may be corrupt, incompetent, or simply human. It stifles the creativity and initiative that are needed to solve novel problems, and eventually it provokes revolution, which is itself a violent upheaval. The history of every authoritarian regime on Earth shows that they either collapse from internal decay or are overthrown by the people they oppress. On a generation ship, either outcome could be lethal for everyone aboard. Democracy is not obviously better. Democratic systems are slow, contentious, and vulnerable to populism, demagoguery, and faction. In a crisis, which on a generation ship could happen at any time, democratic processes may be too slow to respond effectively. And democratic societies can vote to do profoundly stupid things, including abandoning the maintenance schedule, redistributing critical resources based on political popularity rather than need, or even turning the ship around, which is almost certainly physically impossible, but that has never stopped a desperate populace from demanding it. There has also been serious discussion about AI governance, delegating the management of the ship to an artificial intelligence that is presumably immune to corruption, ego fatigue, and bias. But this assumes that the AI remains aligned with human interests for 250 years. The alignment problem, ensuring that an AI continues to pursue the goals its creators intended even as circumstances change, is one of the most challenging unsolved problems in computer science. An AI that was designed to optimize for crew survival might eventually decide that the most efficient path to survival involves decisions that the crew would find abhorrent, reducing population through enforced sterilization, for example, or eliminating individuals deemed genetically unfit. And if the AI controls the life support systems, the locks, the communications, who exactly is going to stop it? Let me shift now to something that sounds prosaic compared to cosmic radiation and genetic death spirals, but is actually one of the most certain and least escapable threats to a generation ship. I want to talk about engineering failure, the simple and relentless truth that machines break down. There has never been a human-made machine that operated continuously for 250 years without major repair or replacement. Not one. The oldest continuously operating machines on Earth, things like medieval clocks and water mills, have survived only because they were continuously repaired and rebuilt by skilled craftspeople using materials sourced from the surrounding environment. On a generation ship, there is no surrounding environment. Every replacement part must be either carried from Earth or manufactured on board. Every tool needed for repair must be maintained, and the tools used to maintain those tools must also be maintained, in an infinite regression of maintenance requirements. Consider the structural integrity of the ship itself. A generation ship would almost certainly use rotation to generate artificial gravity, spinning the habitable sections to create centrifugal force that mimics gravitational pull. This is the only proven method for generating sustained artificial gravity, and without it, the crew would suffer the devastating effects of microgravity, bone density loss of approximately 1% per month, muscle atrophy, cardiovascular deconditioning, vision impairment from intracranial pressure changes, and immune system disruption. After a few generations in microgravity, the humans on board might be physically incapable of walking on a planetary surface, even if they reach their destination. But rotation creates its own engineering nightmare. The bearings and mechanisms that allow the habitable section to rotate must function under continuous mechanical stress for 250 years. At a rotation rate of 1 revolution per minute, which is typical for large habitat designs, the structure completes about 525,000 rotations per year, or roughly 131 million rotations over the course of the journey. Every rotation is a stress cycle on every structural member, every weld, every joint, every seal. Metal fatigue, the process by which repeated stress cycles cause microscopic cracks that slowly propagate through a material until it fractures, is one of the most well-understood failure mechanisms in engineering. The stress cycle count for a generation ship's rotating structure is in the 100 million range, which is firmly in the regime where fatigue failures are not a matter of if, but when. The welds and joints are the weakest points. Even the best welds contain microscopic defects, inclusions, porosity, slight misalignments that act as stress concentrators where cracks nucleate and grow. Inspection technologies exist that can detect these cracks before they become dangerous, but they require trained technicians, functioning equipment, and a culture of rigorous quality control. If any of these degrade over the generations, fatigue cracks that should have been caught and repaired will grow until a structural member fails. And in a rotating pressurized habitat, a structural failure is not a minor inconvenience. It is a potential explosive decompression that can kill everyone in the affected section. Then there is corrosion. The habitable environment of a generation ship necessarily contains water in liquid form for drinking, washing, agriculture, and industrial processes. It contains organic acids from food preparation and waste decomposition. It contains salt from human sweat and urine. It contains oxygen, nitrogen, and carbon dioxide. This is a chemically active environment, and it will attack metal surfaces continuously. Stainless steel resists corrosion better than most metals, but it is not immune, especially at weld joints and stress points, where the protective chromium oxide layer is disrupted. Aluminum, which is lightweight and useful for structural applications, corrodes readily in humid, salty environments. Titanium is more resistant, but much more expensive and harder to work with. Whatever materials are chosen, the relentless chemistry of a wet, oxygen-rich, salt-containing atmosphere will slowly degrade them over decades and centuries. The spare parts problem is perhaps the most practically relevant engineering challenge. You cannot anticipate every component that might fail over 250 years. You cannot carry enough spare parts for every eventuality because the mass budget is too tight. So you need onboard manufacturing capability, the ability to fabricate replacement parts from raw materials. This requires machine tools, metallurgical equipment, casting and forging capability, precision machining, electronics fabrication, and the raw materials to feed all of these processes. It also requires trained operators for every generation, people who can diagnose a problem, design a solution, fabricate the parts, and install them correctly. The institutional knowledge required for this is enormous, and it must be transmitted perfectly from generation to generation. Consider what happens when a critical component fails, and the repair requires a skill or a tool that the current generation does not possess. Perhaps the original engineers who designed the water recycling system used a specific type of ceramic membrane filter that was manufactured on Earth using a process that was documented in the technical manuals, but has never actually been performed on the ship. 150 years into the journey, the last spare filter fails. The current crew has the documentation but not the hands-on experience. They attempt to manufacture a replacement and get it slightly wrong. Perhaps the pore size is a bit too large, allowing some contaminants through. Water quality declines. Illness increases. Agricultural yields drop because the irrigation water is now slightly contaminated. A small failure in one component cascades through the entire system because everything is connected. This cascading failure dynamic is the true engineering horror of a generation ship. Unlike a city on Earth, where a broken water main is an inconvenience that can be repaired while people buy bottled water from the store, on a generation ship, every critical system is the only one there is. There is no redundancy from external sources. There is no just buy a new one. There is the system you have, the spares you carried, and the ability of your crew to fix whatever breaks. When that ability is exhausted, when the last spare is used, when the manufacturing capability cannot replicate the needed part, you are in a situation from which there is no recovery. Power generation deserves special attention because it underpins every other system on the ship. Without power, there is no life support, no water recycling, no agricultural lighting. No rotation for artificial gravity, no computers, no communications, no heating in the cold sections, no cooling in the hot sections. The ship is dead. The most frequently proposed power source for a generation ship is nuclear fission, using uranium or thorium reactors that can provide megawatts of steady electrical power. But fission reactors require fuel that is consumed and must be replaced. A typical reactor fuel load lasts 4 to 6 years before the fuel rods must be swapped. Over 250 years, that is 50 or more fuel changes. Each change requires fresh fuel, which must be either carried from Earth or bred on board using breeder reactor technology. Breeder reactors can produce more fissile material than they consume by converting fertile isotopes like uranium-238 or thorium-232 into fissile plutonium-239 or uranium-233, but they are technologically complex, potentially dangerous, and have a troubled history even on Earth. The reactor itself, with its pressure vessel, coolant loops, heat exchangers, turbines, generators, and control systems, must be maintained for a quarter millennium. Reactor vessels become embrittled over time from neutron bombardment. Coolant pipes corrode and develop leaks. Control mechanisms wear out. Every component of the nuclear power system is a potential single point of failure for the entire ship. Radioisotope thermoelectric generators, like those powering the Voyager probes, are simpler and have fewer moving parts, but they produce far too little power for a generation ship, and their fuel decays predictably. Plutonium-238, the standard RTG fuel, has a half-life of 87.7 years. After 250 years, less than 15% of the original radioactive material remains, and the power output has declined proportionally. Solar power is useless in interstellar space, where the nearest star is light years away. Fusion power, if it could be made to work, would be ideal because the fuel, hydrogen, is abundant, and the energy output is enormous. But controlled nuclear fusion has been 20 years away for the past 70 years. And even if it is achieved on Earth, miniaturizing a fusion reactor to fit on a spacecraft, while maintaining it for centuries, presents challenges that are currently beyond our engineering capability. Computer systems on a generation ship face their own unique degradation pathway. Cosmic radiation does not just damage biological DNA. It also damages computer memory and processors through a phenomenon called single-event upsets, where a high-energy particle strikes a transistor and flips a bit from 1 to 0 or 0 to 1. On Earth, this happens occasionally and is corrected by error-checking algorithms. In deep interstellar space, the rate of single-event upsets is much higher, and over time, cumulative radiation damage degrades the physical structure of the semiconductor material itself, causing progressive failure of individual transistors and eventually entire circuits. Hardened electronics are more resistant but not immune, and they are less powerful per unit mass than standard electronics. The computers that run navigation, life support, atmospheric monitoring, agricultural management, medical systems, and communications must function for 250 years in an elevated radiation environment. The software they run must be maintained, debugged, and updated by crew members who may be many generations removed from the original programmers. And then there is a problem that is almost never discussed, but may be the most fundamental of all. I call it the entropy problem, and it is not a technical challenge, but a law of nature. The second law of thermodynamics states that in any closed system, entropy, which you can think of as disorder or the loss of useful energy and organization, always increases over time. A generation ship is by definition a closed system. It cannot exchange significant matter with its environment. It has a finite energy supply, and over time, entropy must increase. Materials degrade. Energy is converted to waste heat that must be radiated into space. Chemical cycles accumulate trace amounts of unusable byproducts. Information is lost as documents degrade, as institutional knowledge fades, as the fidelity of records declines. The ship, in the most fundamental physical sense, is slowly running down. Like a wound clock that cannot be rewound, it is ticking toward a state of maximum entropy, which is another way of saying death. This does not mean that a ship of any finite lifetime is impossible. It means that maintaining a complex life-supporting system in a closed environment requires constant, intelligent, energy-intensive effort to fight entropy, to repair what breaks, to recycle what is used, to maintain what degrades. And that effort must be sustained without interruption for 250 years. Any lapse, any generation that fails to maintain the systems with the necessary rigor, any period of social upheaval that disrupts the maintenance schedules, any loss of technical knowledge that leaves the crew unable to perform critical repairs accelerates the entropy spiral. Once you fall behind, catching up becomes harder because you have fewer resources, less functioning equipment, and less institutional knowledge to work with. The system decays exponentially once the tipping point is crossed. I want to pause here and connect all of these threads because I think there is a tendency to hear about each of these problems individually and think, well, surely smart people can solve that one problem. Radiation? We will figure out better shielding. Genetics? We will bring a bigger population or frozen embryos. Psychology? We will develop better mental health interventions. Agriculture? We will create more robust crops. Engineering? We will use self-repairing materials. And for any single problem in isolation, there might indeed be solutions, or at least partial mitigations. But the terrifying reality of a generation ship is that you do not face these problems in isolation. You face all of them simultaneously, for centuries, in a closed system with no external support. Consider how they interact. Radiation damages both humans and crops. Crop damage reduces food production. Reduced food production causes malnutrition. Malnutrition weakens the immune system. A weakened immune system makes the population more vulnerable to the pathogens that are evolving in the ship's closed microbial ecosystem. A disease outbreak reduces the working population. A reduced working population means deferred maintenance. Deferred maintenance leads to engineering failures. Engineering failures in the agricultural systems further reduce food production. Engineering failures in the water recycling system contaminate the water supply. Contaminated water causes illness. Illness further reduces the working population. Meanwhile, the genetic diversity of the population is declining with each generation, making future generations less robust against both disease and environmental stress. The psychological burden of living in a deteriorating ship, with increasing illness and decreasing food, drives depression, conflict, and loss of motivation. Loss of motivation leads to further deferred maintenance. The ship is caught in a feedback loop of compounding failures, each one making every other problem worse. This is the cascade failure scenario, and it is not speculative. It is a straightforward extrapolation from known science, known engineering, known psychology, and known biology. Every individual risk factor I have described is well documented and well understood. The only question is how quickly the cascade develops, and whether there is any combination of technologies and social structures that could forestall it long enough to complete a multi-century journey. The honest scientific assessment, based on everything we currently know, is that the answer is probably no. Not with today's technology. Not with technology we can reasonably project for the next century. Perhaps not ever, unless our understanding of physics, biology, and engineering undergoes transformations that we cannot currently envision. Let me walk you through what the cascade failure might actually look like as a timeline, because I think it helps to see the concrete progression from a functioning ship to a tomb. The ship departs Earth with great fanfare. The crew is carefully selected, highly trained, deeply motivated. The systems are new and functioning at peak efficiency. The first decade is, by all accounts, a success. Minor problems arise and are quickly solved. The crew establishes routines for maintenance, agriculture, education, and social life. Children are born, the first generation of shipborne humans. By year 30, the ship is still functioning well, but the first signs of long-term challenges are appearing. The crop yields in Dome 2 are slightly below projections for the third consecutive year. An analysis reveals that the soil microbiome has shifted, with certain beneficial fungal populations declining. The agricultural team implements corrective measures, adding microbial supplements from the biological reserve stocks. It works, but the reserve stocks are now slightly depleted. At the same time, the ship's medical team reports the first cases of a respiratory illness caused by a bacterial strain that shows partial resistance to 2 of the ship's 12 stockpiled antibiotics. The illness is mild and resolves on its own, but the medical team notes the development with concern. By year 50, the second generation is reaching adulthood, and they are different from their parents in subtle but important ways. They have never seen Earth. They grew up in artificial gravity, under artificial light, eating food grown in enclosed domes. Their bone density is slightly lower than Earth norms despite the artificial gravity, suggesting that the rotation-generated centrifugal force is not a perfect substitute for planetary gravity. Their gut microbiomes are less diverse than their parents, reflecting the simplified microbial environment of the ship. Psychological assessments show elevated rates of anxiety and mild depression compared to the first generation. The ship's genetic management program has begun to flag concerns about reduced allelic diversity in immune system genes. By year 80, the third generation is being born, and the cascade is beginning. The water recycling system's primary membrane filters are degrading faster than expected, due to a chemical interaction with a trace contaminant that was not present in the original water supply, but has accumulated over decades of imperfect recycling. The filters are replaced with spares, but the spares were manufactured on Earth 80 years ago, and their performance is slightly degraded from decades of storage. Water quality drops by a measurable amount. The agricultural team reports that crop yields have been declining at a rate of about 1% per year for the past decade, a trend they cannot fully reverse despite their best efforts. The soil is slowly losing organic matter and microbial diversity. The ship's biologist warns that the ecosystem is simplifying, a term that in ecology is synonymous with dying. The third generation, born into a ship that is visibly aging, that smells slightly different than the historical records say it should, where the food is a little less varied than it was in their grandparents' time, is growing up with a deep and pervasive sense of unease. The first organized protest occurs in year 83, when a group of young adults demands a right to turn back. They are told, truthfully, that turning back is physically impossible. The ship does not carry enough fuel for a course reversal. They do not take this well. By year 100 years into the journey and roughly 150 years from the destination, the situation has deteriorated significantly. A severe fungal blight destroys 40% of the wheat crop in Dome 4. The compartmentalization protocols prevent it from spreading to other domes, but the food supply is now critically strained. Rationing is imposed. The population, now in its fourth generation, has experienced its first genuine food shortage. Malnutrition weakens the most vulnerable, the very young, and the very old, and the medical team reports a spike in infections as immune systems are compromised. Meanwhile, the genetic monitoring system shows that inbreeding coefficients have risen above the threshold that was considered safe in the original mission parameters. Several genetic diseases that were rare in the founding population, including a cardiac condition and a metabolic disorder, are now appearing at significantly elevated rates. The frozen genetic bank is accessed for the first time to introduce new alleles through assisted reproduction, but the procedure requires functioning IVF equipment that has not been used in decades and requires recalibration. By year 120, the social fabric is fraying badly. The middle generation problem has arrived in full force. The current adult population was born on the ship, will die on the ship, and has no personal connection to either Earth or the destination. Depression rates have tripled compared to the first generation. Drug and alcohol production, using diverted agricultural products, has become an open problem. 2 violent incidents in the past year have resulted in deaths, the first homicides in the ship's history. The governing council is split between those who advocate for tighter authoritarian control and those who argue for more individual freedom. The debate becomes a proxy for deeper social divisions between different sections of the ship, different work roles, different family lineages. The word mutiny begins to appear in private communications. By year 150, the halfway point of the journey, a pandemic sweeps the ship. A novel pathogen, a bacterium that evolved from the ship's own environmental microbiome, exploiting the weakened immune systems of a malnourished population with reduced genetic diversity, kills 12% of the population over an 8-month period. The medical system is overwhelmed. The antibiotic stocks are depleted against a strain that is resistant to most of them. The surviving population is traumatized, grief-stricken, and deeply divided over the handling of the crisis. The agricultural workforce has been reduced to the point where some domes are running on skeleton crews, further depressing food production. The engineering maintenance backlog has grown to the point where some non-critical systems have been abandoned, their functions either lost or jury-rigged with improvised replacements that work but are less efficient and less reliable than the originals. By year 180, the ship is in serious trouble. A failure in the primary reactor cooling system requires an emergency shutdown and repair that takes 6 weeks. During those 6 weeks, the ship runs on backup power at 60% capacity. The agricultural lighting is reduced, slowing plant growth. The water recycling operates at reduced throughput, requiring strict conservation measures. The rotation speed is reduced to save power, lowering the effective gravity and causing discomfort and disorientation throughout the ship. The repair is eventually successful, but the experience exposes how fragile the ship's systems have become and how thin the safety margins are. The population now in its 7th generation, numbers 700 down from the original 1,000. Genetic diversity has declined to the point where the ship's genetic monitoring system flags multiple population-wide vulnerabilities. The frozen genetic bank, now 180 years old, shows signs of degradation. A sample test reveals that only about 60% of the stored genetic material is still viable. By year 200, the ship that left Earth 2 centuries ago is barely recognizable. The interior shows the wear of 200 years of continuous habitation, scratched walls, patched pipes, jury-rigged electrical connections, agricultural domes running at reduced capacity with visibly depleted soil, lighting panels that flicker because the power grid is being pushed beyond its design limits. The population has stabilized at around 500 after the pandemic and subsequent decline, but 500 is below the minimum viable population for genetic health. Inbreeding depression is now clinically apparent. Fertility rates have dropped. Infant mortality has risen. The average cognitive test scores of the 8th generation are measurably lower than the 1st generation. Though it is unclear how much of this is genetic, how much is nutritional, and how much is environmental. The social structure has devolved into something resembling a feudal system, with the engineering and medical castes holding power over the agricultural and maintenance workers. The democratic governance envisioned by the ship's founders has been dead for generations. By year 220, the situation is dire. The oxygen level in the main habitat has dropped to 18.5%. Due to declining plant photosynthesis and increasing soil respiration. People are not yet in danger of suffocation, but they are chronically fatigued and cognitively impaired. The remaining population of 400 is experiencing the compounded effects of generations of radiation exposure, genetic drift, nutritional deficiency, and psychological stress. The ship's computer systems are failing intermittently due to cumulative radiation damage, and the current generation lacks the programming expertise to diagnose and repair the software problems. Navigation is being maintained by dead reckoning and infrequent star sightings because the primary navigation computer has been offline for 3 years. By year 250, the ship arrives in the destination star system. 47 people are alive, they are malnourished, genetically compromised, psychologically broken, and technically unable to operate most of the ship's remaining systems. The agricultural domes are producing enough food for perhaps 100 people, but there are only 47 left to eat it. The irony is bitter. They have reached the stars, they have traveled further than any human being in history, and they are too few, too sick, too damaged, and too poorly equipped to do anything with their achievement. The planet orbiting the destination star may or may not be habitable. The robotic probes that were supposed to prepare it arrived decades ago, and their status is unknown because the communication systems failed years back. Even if the planet is perfect, even if it has breathable air and drinkable water and fertile soil, 47 people with the genetic diversity of an inbred royal family and the technical knowledge of medieval peasants are not going to establish a thriving colony. They are going to die, probably within a generation or two. The generation ship has not delivered humanity to the stars, it has delivered a funeral procession. And then the ship, empty now or carrying a handful of survivors too weak to do more than wait for the end, drifts on. It passes through the star system, its velocity too great for the feeble maneuvering thrusters to capture it into orbit. It continues into the interstellar void on the other side. And it keeps going, for millions of years. For hundreds of millions of years. A metal coffin carrying the frozen remains of 10 generations of human beings, tumbling slowly through the galaxy, orbiting the galactic center once every 230 million years, occasionally passing within a few light years of other stars, but never close enough for gravity to capture it. A tomb among the stars, the most expensive, most ambitious, most heartbreaking monument ever built by the species that dreamed of reaching for the heavens. This is what I mean when I say that generation ships would become tombs, not because of any single failure, not because of any one problem that a clever engineer or a brave captain could solve, but because the universe is hostile to complex systems in a way that most people do not intuitively understand. Complexity requires energy to maintain. It requires constant input, constant repair, constant vigilance. On Earth, that energy comes from the sun. That repair comes from the billions of organisms that maintain the biosphere. That vigilance is provided by the diversity and redundancy of a planetary ecosystem. Take all of that away, seal 1,000 people in a metal tube, and ask them to maintain a civilization for a quarter millennium with no external support, and you're asking them to do something that the laws of physics, the principles of biology, and the patterns of human psychology all suggest is impossible. But I do not want to end there, because the dream of reaching the stars is not a foolish dream. It is one of the most magnificent and most human dreams there is. And the fact that it is impossibly difficult with our current technology does not mean it is impossible forever. So, let me talk about what the path forward might actually look like, honestly and realistically, without the false optimism that pervades so much popular discussion of space travel. The first thing to acknowledge is that we are not ready. We are not even close to ready. We have not demonstrated the ability to maintain a sealed ecosystem for more than 2 years, Biosphere 2, and even that was a failure. We have not sent a human being further than the Moon, which is roughly 1.3 light seconds away, let alone the 4.24 light years to the nearest star. We have not even established a permanent self-sustaining human presence on another body in our own solar system. We are at the very beginning of a journey that will take centuries before generation ships are even a realistic possibility. And that is okay, because the journey to the stars begins not with a ship launch, but with a series of intermediate steps, each one building the knowledge and capability needed for the next. Step 1 is achieving sustainability on Earth itself. Kim Stanley Robinson, the acclaimed science fiction author who has written more rigorously about generation ships than almost anyone else in fiction or non-fiction, has argued persuasively that the prerequisite for interstellar travel is a sustainable civilization on our home planet. If we cannot manage the resources of an entire planet with its vast oceans, forests, atmosphere and biodiversity, then we certainly cannot manage the resources of a tin can in interstellar space. The skills and technologies needed to create a truly sustainable civilization, perfect recycling, renewable energy, stable governance, equitable resource distribution, ecological management, are exactly the same skills and technologies needed for a generation ship. Earth is our testbed. Step 2 is establishing permanent human presence in near-Earth space. Orbital habitats that test sealed ecosystem technologies with increasing populations and decreasing dependence on Earth resupply. The International Space Station is a primitive first step, but it is entirely dependent on regular resupply from Earth and can support only a handful of people. We need to build stations that support hundreds, then thousands, for years and then decades, with progressively greater closure of their resource loops. Each of these stations will teach us something about the challenges of maintaining complex life support systems in space, and each lesson learned is a lesson that does not have to be learned the hard way during an interstellar voyage. Step 3 is settling the Moon and Mars. These are environments hostile enough to test our technology rigorously, but close enough to Earth that failure is recoverable. A sealed agricultural dome on Mars that fails can be resupplied from Earth within months. The same dome in interstellar space is done for. Mars in particular is an excellent testbed because it requires nearly the same degree of self-sufficiency as an interstellar ship, but with a safety net of proximity to Earth. If we can build a self-sustaining colony on Mars that can survive for 50 years without any resupply from Earth, we will have demonstrated a level of closed system sustainability that is a credible foundation for interstellar travel planning. Step 4 is pushing further into the solar system. Asteroid belt colonies. Settlements in the outer solar system. Each step takes us further from Earth, increases the communication delay, reduces the possibility of rapid resupply, and forces greater self-sufficiency. A colony in the Kuiper Belt, light hours from Earth, operating independently for decades, would be a genuine precursor to an interstellar generation ship. It would face many of the same challenges: limited resources, closed ecosystems, small populations, long communication delays, psychological isolation. But it would still be within the solar system, still reachable by rescue if needed, still close enough to the sun for solar power, and within range of resupply missions that take months rather than centuries. Step 5, and only Step 5, is the interstellar probe. Not a crude ship, but a robotic probe, perhaps a small fast craft propelled by a laser sail. Like the breakthrough starshot concept, such a probe could reach the nearest stars within decades and send back data about the destination star system, its planets, their atmospheres, their potential for supporting life. This information is essential before we commit thousands of human lives to a one-way journey to a destination we have only observed through telescopes. We need to know what is there before we go.